Hey guys, this is your next set of notes for Unit 6. Today we're going to be talking about colligative properties. A colligative property depends on the amount of the substance added, so the more of that substance that you add, the more the properties are going to change. The four main colligative properties that we're going to discuss is freezing point depression, boiling point elevation, vapor pressure reduction, and osmotic pressure reduction. That last one we won't really go into detail about, but I just want you to know that it is something that's there. When you add a substance to any liquid, you make it harder for that liquid to freeze, boil, or evaporate. The substance physically blocks the liquid from one of those things, freezing, boiling, or evaporating. The liquid has to get colder to freeze, so it has to get warmer to boil, or it won't evaporate as much when you start adding something to it. So that's why when we add salts to the streets in the winter, the reason why is the salt blocks the water from freezing, or it just means that it has to be colder for the water to freeze and make ice on the road. Adding salt to boiling water for spaghetti makes it take longer for the boil to water, not shorter. So I know a lot of people think adding salt to your water makes it boil faster, but it actually just makes it boil at a higher temperature. The salt prevents the water molecules from being able to transition from the liquid to the gas phase as quickly. Here are the equations that you need to know. We'll talk about each one. Again, that last one we won't really go into detail about right now. I, lowercase I, or the Van 't Hoff factor, is the number of particles a molecule will break into in a solution. If it's a covalent molecule, meaning it's all nonmetals, it will not break up in water, so their I value is just 1. That's because covalent molecules don't ionize. They're not made up of ions. Covalent molecules have no total charge. Water is not going to be able to pull them apart into ions. So just pay attention to what the molecule is. If it's covalent, I equals 1. Here's an example of that. So on the left, I have C6H12O6. All of those are nonmetals. That's covalent. It's not going to be broken apart in water, so I equals 1. NaCl is ionic. It can be split into sodium and chlorine separately. So that's 2 molecules that are floating around now, 2 ions. So I equals 2. Next I have CaCl2. That's also ionic. It can be broken apart into 3 ions. So I equals 3. Common solvents and their freezing point and boiling point constants. Okay, so you're going to see a chart on my next slide, and this is what it is. The constant indirectly tells us how difficult it is to change the freezing point or the boiling point. The smaller that constant is, the more difficult it is to change the freezing or boiling point. Notice that water has the smallest of these due to strong hydrogen bonding, so it's going to be difficult to change the freezing and the boiling point of water. So here's that chart of a few common solvents over there on the left. What I'm looking at is Kf and Kb. Water has the smallest of those numbers because of that strong hydrogen bonding. So this chart, it might be good to take a screenshot of because it will be useful to you as you do the practice problems today. Okay, freezing point depression. Delta Tf is your change in freezing point. Kf is the freezing point constant for the liquid. M is the molality, which we'll talk about that in a second. I is the Van 't Hoff factor. Freezing point will always go down when something blocks the liquid because the liquid must lose even more energy in order to rearrange themselves around the substance that's blocking it. Okay, salt is used to de-ice the streets in the winter. If we need to lower the melting point of ice on the streets by 6 degrees on a given evening, how many grams of salt need to be added to 200 kilograms of ice on a given street? So we're going to use this equation. This time I know delta T, but generally that's what you're going to be trying to find. So delta T is 6. Kf, I can look back on my chart for water and figure out what Kf is. We're looking at NaCl, so we need to figure out how many ions NaCl will make for I. And then M is molality, which we'll need to solve for. I is going to be 2 because sodium and chlorine will split apart into their ions, so I have 2 ions. So I can plug it in and it looks like this. The 1.86 comes from that chart that I asked you to screenshot, and that's just the KF constant for water. Okay, so I can go ahead and solve this equation. This is giving me 1.613 m. This I can use to find my number of moles. So if I set it up equal to 1 kilogram of ice, I can say that 1.613 moles of salt over 1 kilogram of ice equals 1.613. But if I'm trying to figure out how many moles of salt I have for 200 kilograms of ice, I can set up this proportion. Then I'm just going to cross multiply 1.613 times 200. So when I do that, I got 322.6 moles. I needed to convert to grams, so I multiply by the molar mass of NaCl. To get that, it would be 18,855.97 grams. That's my answer. Next, we have boiling point elevation. Delta TB is a change in boiling point. KB is the boiling point constant for the liquid. M is still molality. I is still the Van't Hoff factor. Boiling point will always go up when something blocks the liquid because the liquid has to gain even more energy in order to arrange themselves around the substance that's blocking it. So in order to go from the liquid phase into the gas phase. So in these questions, your answer should be higher than the original boiling point was. Let's do an example. Saffrol is contained in oil of sassafras and was once used to flavor root beer. So that's just an essential oil. A 2.39 gram sample of saffrol was dissolved in 103 grams of chloroform. What's the new freezing point of the chloroform? Saffrol has a molecular formula of C10H10O2. So here is my equation. Those should say delta TF, not B. I don't know why it says that. I is just 1 because this chemical is covalent, so it's not going to break apart into ions. So I equals 1. Chloroform has a boiling point constant of 3.63. That should say freezing point constant. It has a freezing point constant of 3.63. That's straight from the chart. We need to convert grams of saffrol into moles of saffrol to be able to plug it into the molality equation. So if I'm converting into moles, I'm taking my 2.39 grams, dividing it by the molar mass of that whole thing, which is 162.19, and I get 0.01474 moles of saffrol. So this is not molality. I still can't plug it in. Molality is going to be your moles of saffrol over your kilograms of the liquid. Okay, so here's what I was saying. I have moles of saffrol over my grams of chloroform, so which it's converted into kilograms. I divided the grams by 1,000 to get this number, and then I get 0.1431. That can now be plugged into my original equation and will look like this. That gives me a change in temperature of 0.519. So that's just the change. I want to know the total temperature of the saffrol plus the chloroform, so I need to go ahead and add those together, and I would get 61.7. Next we have Raoult's law. I know this one is not on your notes, so just pay attention. It might help to write a little bit of this down. So I have vapor pressure new equals vapor pressure old times X. X is the mole fraction of the liquid, not of the solid, it's the liquid. Vapor pressure always is reduced when something blocks the liquid because it's harder for a liquid to evaporate when there's other particles blocking it from doing so. So let's do an example. Camphor is the main medicinal ingredient in Vicks VapoRub. The vapor pressure of pure benzene is 100 millimeters of mercury at 26.1 degrees Celsius. Calculate the vapor pressure of a solution containing 24.6 grams of camphor dissolved in 98.5 grams of benzene. So here's my equation. I'm looking for VP new. I know VP old is 100. I need to figure out X so I can solve this. X is your mole fraction. So it's going to be my moles of benzene over the total moles, so benzene plus camphor. First thing I want to do is convert grams of benzene into moles. So I'm going to do 98.5. Oh, they did camphor first, but I was saying benzene, so we'll come back to benzene. So same thing though, I'm converting grams of camphor into moles. 24.6 divided by its molar mass gives me 0.1616. So we'll come back to that number in just a second. We need to do the same thing with benzene. We're converting our amount of benzene into moles, so I'm dividing by the molar mass. So C6H6, the mass of that is 78.1. So now I have the moles of benzene. I can put that number over my total number of moles. So if you add the moles of camphor and the moles of benzene together, you would get 1.4226. So my fraction would look like this. That gives me 0.8864. That is X. I can now plug that back into my formula, and it looks like this here at the bottom. 100 times 0.8864 gives me my new vapor pressure as 88.6. Okay guys, that's it. If y'all have questions,